All right, ready to dive into something a little
Oh,
unexpected.
I love unexpected.
Today's deep dive, the math behind necklaces and bracelets.
Necklaces and bracelets.
Yeah, I know. Sounds kind of kindergarten-y.
Yeah, right.
But trust me, this gets complex and fascinating. Fast.
Oh, I believe it. Math can hide anywhere.
Exactly. And we're not talking about actual jewelry here.
No.
Nope. In combinatorics, necklace and bracelet are all about arranging objects in a circle.
Okay, so like a pattern, not the jewelry itself.
Exactly. And with bracelets, there's an added twist reflections.
Ooh, like mirror images.
Precisely. To guide us, we've got excerpts from two sources.
Let's hear them.
First, the Online Encyclopedia of Integer Sequences, or OEIS.
The OEIS?
Yeah, it's this giant database of integer sequences.
Full of mathy goodness, I bet.
Oh, yeah. And second, we've got the Wikipedia article on necklace and bracelet counting.
So two perspectives on the same concept. Cool.
Exactly. So, mission briefing time. By the end of this deep dive, you'll be able to look at a necklace or bracelet.
And see more than just beads.
Yep. You'll see the mathematical principles at play. But first, basics. What is a necklace in this mathematical sense?
Imagine a string of beads in a circle.
Okay, got it.
Now, if you rotate that string and it looks the same as another arrangement, they're considered the same necklace.
Ah, so it's the arrangement,
Yeah.
not the specific position of each bead.
Exactly. Think of a clock face, move the hour hand. It's still the same clock, just a different time.
Makes sense. So what makes a bracelet different? Just the flipping.
Exactly. With bracelets, reflections matter.
Okay, so if I flip it and it looks different, that's a separate bracelet.
You got it. It's like your left and right hand.
Mirror images, but not the same. I'm picturing this. So if I have a bracelet, say, 3 red beads, 3 green beads,
Yeah,
just by flipping, I might make a new arrangement.
you got it. And the Wikipedia article has a cool example.
Ooh, tell me.
Imagine 3 bracelets, all 3 red beads, 3 green.
Okay, visualizing it.
2 of them, when you rotate them, become the same. So one necklace.
Right, because rotation doesn't make them unique.
Exactly. But the third one is special. It's chiral.
Chiral, like
Yeah.
my hands again, not symmetrical.
Exactly. Flip this chiral bracelet, boom, totally new arrangement. Can't get that just by rotating.
So 3 bracelets, but 4 necklaces.
You got it. Reflections can make things way more complex.
My brain's already hurting a little.
Haha. But it's cool complexity. Now, how do we count all these possibilities? I can't just keep picturing beads forever.
Right, there's got to be a better way.
There is. Enter the OEIS sequences. They're like cheat codes for counting this stuff.
Cheat code's nice.
For example, necklaces with 2 colors. That's sequence A00000009.
Writing this down.
Bracelets. A081720. Plug in the number of beads, bam, you get the number of arrangements.
So it's like a lookup table for all these combinations.
Exactly. But how did they come up with those numbers in the first place? Some serious math must be involved.
I'm ready to get mathy.
All right, first up, Euler's totient function, denoted as finis. It's all about counting numbers that are relatively prime to a given number.
Relatively prime. Remind me what that is.
It means 2 numbers share no common divisors other than 1.
Okay.
Like 8 and 15 are relatively prime. Only 1 divides into both evenly.
So they're like mathematical strangers only connected by the number 1.
Exactly. Euler's totient function tells you how many of those strangers exist for a given number.
Okay, I'm with you so far. But what does this have to do with necklaces?
Ah, the magic is about to happen. Imagine a necklace with, say, 6 beads.
6 beads, yeah.
Euler's totient function helps us count only the unique rotations of this necklace.
Because we don't want to count the same arrangement multiple times just because we spun it around.
Precisely. And this is where divisors come in?
Divisors.
Yeah.
Like numbers that divide evenly into another number.
Exactly. For 6, the divisors are 1, 2, 3, and 6. Think of them as different ways to jump around our necklace.
Jump around.
Yeah. Like jumping by 2 beads gives you a different pattern than jumping by 3, right?
Oh, I see. So divisors are like different step sizes for moving around the necklace. And some steps create the same arrangement, which is where Euler's totient function helps us.
Precisely. It eliminates rotations that don't create unique arrangements.
So it's like a filter, getting rid of the duplicates, leaving us with only the truly unique necklaces.
Exactly. A mathematical sieve for necklaces.
Wow, that's pretty neat. Euler and divisors working together.
Teamwork makes the dream work. What else do we need to count necklaces and bracelets?
Lay it on me.
Multinomial coefficients. They're all about counting arrangements when we have different types of objects.
Different types, like in our case, beads of different colors.
You got it. They tell us how many ways to arrange things when order matters, which is key for necklaces and bracelets.
Okay, multinomial coefficients. Vaguely ringing a bell from high school.
They involve factorials, if that helps jog your memory.
Ah, factorials, right. Those things that get big really fast.
Yeah, they help us figure out, for example, if we have 2 red, 2 yellow, and 2 green beads.
How many different necklaces we can create.
Exactly. Like having different buckets for each color, and the multinomial coefficient tells us how many ways to fill those buckets to make a unique necklace.
Okay, starting to click. This is already way more complex than I initially thought. Anything else we need to consider?
One more concept. Sterling numbers of the second kind.
Sterling numbers. Sounds intimidating.
Don't worry, they're just a fancy way of dealing with a specific situation. Imagine you have a set of colors and you want to use all of them in your necklace or bracelet.
Use all of them, okay.
Sterling numbers tell us how many ways we can divide our beads into groups of different colors, making sure every color is used.
So not just arranging, but grouping by color, making sure no color gets left out.
Precisely. Adds a whole new layer of complexity. And it has real-world applications, too.
Like what?
Like figuring out how many ways you can form committees with diverse representation.
Whoa, from beads to committees. This math is reaching everywhere.
But for now, back to the beads. Remember those 3 red and 3 green bead bracelets?
Yeah, the ones where 2 were the same necklace and 1 was chiral.
We can use the formulas from our sources and the concepts we just discussed to calculate the number of possible necklaces.
Wait, really? Show me how that works.
All right, so with those bracelets, we ended up with 4 distinct necklaces, right?
Yep, because of that chiral one.
The formula for counting necklaces uses Euler's totient function and the number of colors. If we plug in n equals 6 for the total beads and k equals 2 for our 2 colors,
What does the formula give us?
it spits out the number 4.
Whoa, so the formula actually predicted what we saw with the beads. That's pretty wild.
It is, right. And it gets even cooler with more complex examples. Remember those 11 bracelets with 2 red, 2 yellow, and 2 green beads?
Yeah, those were a mouthful.
The Wikipedia article shows us there are 16 distinct necklaces possible from those.
16 necklaces from 11 bracelets. Some chiral trickery going on there.
You bet. 5 of those 11 bracelets are chiral, meaning their reflections create unique necklaces, hence the higher count.
Okay, so reflections really mess with the numbers. I'm starting to see how powerful these formulas are.
They might look scary, but they're just tools to help us make sense of these arrangements.
Exactly. Tools to unlock the patterns. But wait, we've only talked about necklaces so far. What about bracelets and their reflections? They must have their own formula, right?
You're right. Bracelets do have their own special formula, building on the necklace one. It takes into account whether the number of beads is even or odd, because that affects how reflections create unique arrangements. But that's a story for the next part of our deep dive.
This is already more than I ever thought I'd know about necklaces and bracelets. I can't wait to see what else we uncover in the next part. Back again, diving deeper into necklaces and bracelets. Still processing all that math from the first part.
Yeah, combinatorics can be a real brain workout, but so cool once you start seeing the patterns.
Speaking of patterns, you mentioned something called aperiodic necklaces before. What are those exactly?
Aperiodic necklaces, they're kind of the rebels of the necklace world.
How so?
Well, remember our necklace definition, where rotations can lead to the same arrangement.
Yeah, like the clock face example.
Exactly. Aperiodic necklaces break that rule. No matter how you rotate them, you always get a unique arrangement.
Every single rotation is a new arrangement. How is that even possible?
It's like snowflakes, each one totally unique. And to count them, we use a special tool, the Mobius function.
Mobius function?
Yeah.
Another mathy name.
Don't let it intimidate you. Think of it as a filter. It sifts through the divisors of n, our number of beads.
Okay, I remember divisors.
And it weeds out any divisors that would lead to repeating patterns, leaving us with only the aperiodic arrangements.
So it's like a super specific sieve, catching only those unique aperiodic necklaces.
You got it. And that leads us to a formula for counting them, represented by m sub n.
M sub, got it. Another formula to add to our collection.
This formula combines the Möbius function with the possible arrangements for each divisor of n.
So it's like a multi-step process, but ultimately it gives us the count of those unique snowflakes.
Exactly. And then we have Linden words.
Linden words. Okay, this is getting even more intriguing. What are those?
Think of them as name tags for each aperiodic necklace.
Name tags. How does that work?
Every aperiodic necklace has one, and only one, Linden word that represents it uniquely.
This is like a code name, a way to identify each unique necklace.
Precisely. Imagine you take all the possible rotations of an aperiodic necklace
Okay, I'm picturing it.
and you arrange them alphabetically.
Alphabetically.
Hmm.
Interesting. The Linden word is simply the one that comes first, alphabetically.
So it's like the smallest version of the necklace, alphabetically, and that somehow acts as a unique ID.
You got it. A neat and elegant way to pin down these unique aperiodic necklaces.
Pretty cool. So we've uncovered this hidden language within necklaces, and Linden words are the key.
Exactly. But this language isn't just for counting. It has uses in cryptography, coding theory, even bioinformatics.
Whoa, from beads to cryptography, that's a big jump. It is. Think about encrypting data, or efficiently storing and retrieving information. Aperiodic necklaces and Linden words play a role in that.
So we can use these tools to not just count arrangements, but to actually work with information in real-world applications. That's amazing.
Math is everywhere once you start looking for it. We can find these principles in everyday scenarios, too.
Okay, I love real-world examples. Give me one.
How about seating arrangements? Imagine a dinner party with 6 guests around a circular table.
Okay, got the scene.
The principles of necklaces and bracelets can help you figure out how many unique seating arrangements are possible.
So if I want every guest to sit next to everyone else at some point during the dinner, I could use those aperiodic arrangements. That's pretty cool.
You got it. Or think about musical patterns. A repeating melody is like a necklace, and variations within that melody, like reflections or periodic segments, can be analyzed using the concepts we've discussed.
So musical patterns as necklaces and bracelets, that's a whole new way to think about music.
And that's the power of mathematics. It gives us a new lens to view the world and appreciate the hidden patterns and structures all around us.
Mind officially blown. This deep dive is making me see everything differently.
We've come a long way from simply counting beads. We've uncovered complex math concepts and seen their real-world applications.
I can't help but wonder, what if we push this even further? We've talked about specific numbers of beads and colors, but what if we had an infinite number of beads or unlimited colors? Does the math still work?
That's a fantastic question. It takes us into the realm of infinite sequences and generating functions.
Infinite sequences, generating functions.
Yeah.
Sounds like a whole other deep dive waiting to happen.
Indeed. But for now, let's enjoy what we've learned about necklaces and bracelets. It's amazing how these simple objects have led us to such profound mathematical insights.
It really is. Before we wrap up this part, what's the main takeaway you want our listeners to remember from our exploration so far?
Never underestimate the power of simple things.
Yeah.
A necklace, a bracelet. These arrangements can open up a world of mathematical beauty and complexity, revealing patterns that govern our world. But there's more to uncover.
That's a great point. We've only just scratched the surface. Stick with us, listeners. When we return, we'll wrap up our deep dive and leave you with a final thought to spark even more curiosity about the fascinating world of combinatorics. And we're back, ready to wrap up our deep dive into the surprisingly deep world of necklaces and bracelets.
You know, it's amazing how much we've uncovered just starting with these simple objects.
We've gone from basic definitions to complex math formulas.
Yeah. And real-world applications, too. But before we finish up,
Ooh, there's more?
there is one final thought I wanted to share, something that builds on what we've talked about.
Okay, I'm all ears.
So we've mostly focused on necklaces and bracelets as linear arrangements, right? Beads on a string.
Yeah, that's been our visual so far.
But what if we take this idea to higher dimensions?
Higher dimensions. You mean like 3D necklaces?
Yeah.
4D bracelets?
Whoa. Exactly. Imagine a necklace arranged on the surface of a sphere, or a bracelet in a 4-dimensional space.
Okay, my brain's trying to picture that.
It gets wild.
Yeah.
But the principles we've discussed, rotations, reflections, aperiodicity, they all still apply.
They do.
Yeah. But they become even more complex and interesting in higher dimensions.
So we could have spherical necklaces, hypercubic bracelets. The possibilities are endless.
Exactly. And the math tools we've used would need to be adjusted to handle these higher dimensional arrangements.
So Euler's totient function, multinomial coefficients, the Mobius function, they all get an upgrade.
In a way, yes, we'd need to extend those concepts to deal with the added complexity.
This is blowing my mind. So this deep dive wasn't just about necklaces and bracelets.
Yeah.
It was about opening up a whole new way of thinking about arrangements and patterns in multiple dimensions.
Exactly. That's the power of combinatorics, taking a concept and seeing how far you can stretch it.
This has been an incredible journey, from counting beads to pondering higher dimensions.
And hopefully along the way, you've gained a new appreciation for the power and beauty of mathematics.
I know I have. I don't think I'll ever look at a necklace or bracelet the same way again.
That's a good sign. A good deep dive should change your perspective.
It definitely has. So to our listeners, as we wrap up,
Yeah.
here's a challenge. How can these principles of necklaces and bracelets be applied to other circular or cyclic arrangements in the real world?
Oh, good one.
Think about traffic flow in a roundabout, the arrangement of petals in a flower.
Or the cycles of the seasons?
Let your curiosity guide you and see what mathematical connections you can find.
It's all out there, waiting to be discovered.
This has been The Deep Dive, signing off.